Hi everyone. Today we're gonna present our project, Generative Adversarial Networks, MONE and ART, by me, Kirill Kuzmin, and Slava Tsivina. Let's remind what the problem was. Our goal was to build such GAN that generates images in style of some artist. In our case, it was Monet. We took a data set from Kaggle, which consisted of 300 Monet pictures for training and more than 7,000 photos. And the output was more than 7,000 Monet-like pictures. As a baseline model, we took cycle GAN. So what is a cycle GAN? It's a doubled generated adversarial network. Normal generated adversarial network consists of a pair of generator which generates fake image and discriminator which tries to discern real image from fake, and they train each other. In cycle GAN, you have a pair of objects, and eventually you have additional metric to assess the quality of a picture, consistency, cycle loss, which we'll discuss a bit later. Our model use standard U-Net architecture for generator, which you can see here. And discriminator also, just for baseline model, had pretty simple architecture for deep neural networks. So it just takes an image, downsamples it, and stops at the size of 30 by 30 by 1. And for each of those 900 bits, it tells whether this part of image looks like real or looks like fake. Let's discuss how our progress on this work went. So first we built a baseline GAN model. Then we tried to change architecture of generator using pre-trained VGG16 network, but it didn't work well. The details a bit later. Then we tried to remove some layers in the bottleneck, see what the effect is. Didn't work well as well. Then we ask ourselves, why do we need such heavy model as cycle GAN? Maybe we just can stop at just GAN. And we tried, and it worked pretty well. And we thought, okay, maybe we can improve it a little bit further. And we did some augmentation, and we saw that with or without augmentation is kind of comparable with cycle GAN. And then we decided to stop at just GAN with augmentation and improve it a bit further, incorporating the idea from one of the papers. The idea was to implement fully connected layers in just next to the bottleneck in the generator. And that's our final model we're going to discuss. So let's quickly see what the ideas were for layers removal. Just one of the layers removals was like this. We just remove those layers, connect properly, and see what happens. The next idea, it was to just get rid of cycle in cycle GAN. And the rationale was like, why do we need this cycle consistency loss? What is cycle consistency loss? It basically checks whether an image reconstructed from the generated image equals to original one. But even if we have some change in color, for instance, if a tree has different color in this image, it still looks like Monet picture. So maybe it's not that important, we thought. And indeed, it doesn't look that important. Also, we incorporated some augmentation, and it worked pretty well as well. And that's actually the description of the idea with addition of fully connected layers in generator. So here we add fully connected layers, following 5. And now Slava going to describe the rest.
Yeah, I will talk about the evaluation of the models and the results. So for generator loss function, we actually take 2 parts. First, we look into estimation of discriminator of our generated image and want it to be as close to real estimation as possible. We estimated using binary cross entropy, but at the same time, we want the identity between real image and generated image to be pretty small, so that we can see that it was actually close to original image. And for discriminator loss, it also consists of two parts. First part, it needs to estimate real image as close to all ones as possible, and it also needs to estimate fake image as close to all zeros, meaning fake, as possible. And the idea is that if the discriminator loss is close to 0.5, it is ideal, meaning it cannot distinguish between real and fake images. Move on. So here we see graphs how this loss function changed for generator and discriminator over different models for many epochs. And we see that for generator, different model converges on roughly the same value. But for discriminator, our models are closer to 0.5 mark than base model that is in blue. Here is a graph of generator loss for VGG16, and we see that it didn't work out, meaning its loss function didn't increase, and we are not sure why. Finally, there is a so-called Frechet inception distance. It is a standard distance to evaluate the performance of GAN networks. And we compared our solutions against baseline. And we see in highlighted in yellow, there are best solutions, and our final model with fully connected layers performs the best. And now let's look into some results. On the left, you see real photos. Second column is baseline. And last column is our final model. And you can see here, for example, that baseline introduces a lot of repetitive patterns, while in our final form, these patterns are not so obvious. And since most pictures are actually landscapes, when we try to input some particular objects, the network may struggle with it, and we don't see some differences. But also there are particular artifacts that we can still see, such as repetitive patterns for some images. And when we look into particular objects or people, we also can see some strange artifacts. Or sometimes it may not change the picture at all. Yeah. So it is a list of our references.
That's about it. That's the references. And if you have any